You've probably heard that AMP makes your pages fast, to the point where their load time feels almost instant, like the switch here. But how do we do it? How do we get to that ludicrous speed? I'm glad you asked. Here are the top 7 components. Number 1, never stop the content. Take these dominoes here, for example. They represent our load chain, and that's the total amount of time required to load your page. Most websites include assets and scripts that are synchronously downloaded in the order specified, and therefore block the rendering of the page. This could, for instance, be a third-party ad, like this red domino here, that appears between 2 blocks of content and stops the rest of the page from rendering until the ad is fully available. Now, AMP solves this by making all of its own scripts and components load in parallel at the same time. Here we go. And by not allowing any custom JavaScript that could break those rules. Now instead, interactive page features are handled in custom AMP elements. The custom AMP elements may have JavaScript under the hood, but they're carefully designed to make sure they don't hurt performance. Okay, wait a second. No JavaScript at all? Well, one way to get around the limitation are iframes. While third-party JS is allowed in iframes, it still cannot block the main page from rendering. For example, if third-party JS uses a terrible document write API, it does not block rendering the main page. Next. Number 2, asset-independent layout. On a normal HTML page, the browser often doesn't know what the layout will be before all assets are loaded. Take this picture in its raw state. Now, in its raw unloaded state, I have no idea how large it's going to end up being, and if I still have enough space for the rest of my content until it's fully rolled out. In AMP, all external images, or ads, or iframes must state the size in the HTML so that AMP can determine each element's size and position before the actual resource is loaded. So AMP loads the layout of the page without waiting for any resources to download. That's what we call static layouting, and is a crucially important concept in the AMP world. AMP uncouples document layout from resource layout. Only one HTTP request is needed to lay out the entire document. But even with these in place, CSS blocks all rendering and page load. Plus, it tends to get bloated. Which brings me to number 3, inline size-bound CSS. Let's pretend these green dominoes here are our style sheets. Now in AMP pages, we allow only a single style sheet, and that one is inline. Compared to most web pages, this removes one or often more HTTP requests from the critical rendering path. In addition, the inline style sheet has a maximum size of 50 kilobytes. While this size is big enough for very sophisticated pages, it still requires the page author to practice good CSS hygiene. Number 4. Web fonts are super large. So web font optimization is crucial for performance. On a typical page that has a few synchronous scripts and a few external style sheets, the browser waits and waits to start downloading those huge fonts until everything else is done. The AMP system requires 0 HTTP requests until font starts downloading. And this is only possible because all JavaScript in AMP is, like we just learned, asynchronous and only inline style sheets are allowed. Number 5. Minimizing style and layout recalculations. Each time you measure or change something via script on a page, the browser has to lay out and recalculate the page. And these operations get fairly expensive. So assume that those are 2 pictures that are already loaded on the page. When this picture from earlier is half loaded, then the content is over here. But when it's fully loaded, the content is pushed further down. So the browser doesn't know in advance what will happen to the layout of the page until all assets are loaded. Now in most pages, multiple scripts do various dynamic things at the same time, causing lots of relayouts. But because AMP mediates all render operations, it intelligently combines readings and changes to minimize effort. For example, we can get away with just 1 or 2 layouts before the page is displayed. Number 6. GPU-accelerated animations. For the longest time, all work to display a page in a browser was done by your computer's processor or CPU. But it turns out that your graphics card, specifically your GPU, is much more efficient at pushing pixels around. So by offloading a lot of the visual work to the GPU, a browser can free up CPU cycles and make your page run faster. When the CPU layouts a page, it creates so-called layers or textures that are then sent to the GPU for further manipulation. The GPU can take those layers and transform them, for instance, shrink them, fade them, rotate them, move them around, everything what you can imagine, basically. CSS allows you to animate all sorts of CSS properties, but AMP forces you to stay in a fast lane by only allowing those that can happen on the GPU, namely transform and opacity. And finally, number 7. Prioritized resource loading. When AMP downloads resources, it optimizes downloads so that the currently most important resources are downloaded first. Images and ads are only downloaded if they're likely to be seen by the user. Now, above default, or if the user is likely to quickly scroll through them. And so we make a prediction that they will be seen on screen. And remember, we know what's above default because of the previously mentioned static layouting system. AMP also prefetches lazy loaded resources that appear somewhere below default, but are going to be important later. And the key here is that resources are loaded as late as possible, but prefetched as early as possible. That way, things load very fast, but precious CPU cycles are only used when resources are actually shown to users. Now you've learned about 7 smart optimizations that AMP does for your pages. But this only gets us to pretty fast, not instant. So check out some of the other episodes to find out why AMP pages feel like they load instantly. And subscribe for more of this. Get in touch via the comments below or on Twitter. Onwards.